Okay, this video will cover chapter 2, section 5, 6, and 7. Okay, section 5 is to use the derivatives into life applications. So one typical problem is to optimize, so optimization problems, to optimize the situation. So either we find the lowest cost, right, which will have the concept of a minimum. It could be relative minimum, sometimes we call local minimum, or absolute minimum. Right? Usually we want to minimize our cost and maximize our profit. Right? So to make a simple case, let's see, minimum, we're looking for this point. Maximum, we're looking for this point. What's special about those points? If we draw the tangent line, we could draw the tangent line, and the tangent line is horizontal, and tangent line is horizontal, which means the slope of the tangent line is 0, which means the derivative of the function. So the blue color is a function. The derivative at this x value, this typical x value, equals 0. Right? So we're going to use it for both cases. So the derivative of the function at this given point, at such x value, equals to 0. So we're going to use that concept into life applications. Let's see this example. We want to find the minimum value of such function. So what do? So this is a polynomial degree 3, right? The graph looks like this. It wiggles twice. And we want to find the minimum value, which means we need to find this point. Well, this point is 4, 3. So how do we find it? We're going to take a derivative of this function, which is 6x squared minus 30x plus 24. Then we set this derivative function to be 0. Then we solve for x. So 6 is a common factor. So let's factor out 6. Or let's divide by 6, right? Let's just divide every term by 6. Right? So we get x squared minus 5x plus 4 equals to 0. Then we can factor this. We can factor as x minus 1, x minus 4. Because minus 1 times minus 4 give us positive 4. Minus 1 plus minus 4 give us negative 5. Then we use 0 property to solve this. So x minus 1 to be 0, x minus 4 to be 0. Because if we multiply two things to be 0, one of them, at least one of them has to be 0. So x equals 1, x equals 4. Right? We see right here. We see this is x equals 1. That's a local maximum. And the x equals 4 is here. But we need to find the minimum value. Minimum value of the function means f of 4. But how do we know, right? Without this graph, how do we know which one costs maximum, which one costs minimum? So we do this. We draw real number line, right? We mark 1 here. We mark 4 somewhere here. Then these two values split the real number axis into 3 intervals. So we consider from negative infinity up to 1 interval, 1 to 4 interval, and 4 up to positive infinity, right? Positive infinity on this side. So 3 intervals. So we want to see what happens in these 3 intervals. So what do? Typically, we want to remember we have this first derivative test. If the derivative at such x value is positive, that means original function increases, right? If it's negative, original function decreases. So we're going to pick a value on the left-hand side of 1. So we can pick 0. Right, on the left-hand side, smaller than 1, we can pick 0. So in this interval. So in this interval, let me change my color. I want to pick 0 to evaluate. I want to pick maybe 2 to evaluate as long as in the interval. Maybe I pick 5. Actually, since this is a polynomial function, we only have to evaluate the beginning one because it's one piece of string. It wiggles. Right? Okay, so what do? We plug in the derivative function to see if this is positive or negative. Well, that's a 6 times 0 squared minus 30 times 0 plus 24, right? By using this derivative function. Of course, this is first two terms are 0, so that's 24, which is a positive. So positive tells us in this interval. So from negative infinity to 1, the function increases. So because this is a polynomial function, degree 3, right? So once it reaches the local, so at 1, that's a local extremum, right? Because this function increases from the left-hand side, so we know some point here has to be relative maximum. Then 4, of course, it just keeps wiggling, right? At 4, it should be relative minimum. So that's how we find out. Because this is a polynomial function, so we only have to evaluate the beginning one. If it's other functions, we need to find a value, evaluate at each interval. All right, so we know 1 comma 30. How do we get 30 here? We just plug in, right? But in this case, we don't need to find 1 comma 30 point because we are finding minimum value. So we want to find this 3. How do we find this 3? We plug in 4. So now we know this one is a local or relative minimum. So we just have to evaluate this one. We just have to evaluate f of 4. Right? We'll plug into the original function. So it's 2 times 4 raised by 3 minus 15 times 4 squared plus 24 times 4 plus 19. So be very careful. You see, when I evaluate, when I talk about how to find the local maximum, local minimum, I evaluate with the derivative function. But when I want to find the function value at a point, I evaluate the original function. So make sure you evaluate with the right function. Then with these 3, I have 4 as actually these 2, we can do this. We can factor out 4 squared. So I have 1 4. So 2 times 4, that's 8 minus 15. Then plus 24 times 4 plus 19. If you have a calculator, just use your calculator to do this, right? Then 8 minus 15, that's negative 7. So I have 4 squared plus this 2, right? Then I can factor out 4 times negative 28 plus 24, then plus 19. Again, you can use calculator because I'm doing by hand. Okay. So negative 28 plus 24, that's negative 4. 4 times negative 4. Oh, probably made a mistake. Minus 15 times 4 squared. That's right. So I factor out 4 squared, 4 squares. I factor out 4 squared. I have 8 minus 15. That's negative 7. Then I factor out 4 from the factor out this 4. Then I have 4 times negative 7 with a negative 28. Then plus 24. Yes. Right. Okay. That's right. Then plus 19, which is 3. So that's how we got this point. So that's the answer. So the minimum value of this function is f of 4 equals to 3. So 3 is the minimum value, okay, not 4. 4 is x value. When we talk about function value, let's see this question. Suppose that a ball, let me change the color, through straight up into the air and its height after t seconds is such function. They determine how long will it take for the ball to reach its maximum. So just imagine you toss this ball, right, into air, and of course it will drop at a certain point. So what is this point? Well, given this function, right, this function we can write as f of t. We just have to find f prime of t, which is 48 minus 32t. And then we set this one to be 0. Right, that's, we can rewrite as 32t equals to 48. So then we divide by 32 on both sides. So t equals to 48 divided by 32. We can divide by 4, get 12. 8 divided by 4 again is 3 over 2. So after 3 over 2, well, seconds, after 1.5 seconds, the ball will reach its highest height. Right? Do we know? So this only asks how long it takes. Right? And also we need to determine the maximum height, which means we need to plug in 3 over 2 to find its height. So that's 4 plus 48 times 3 over 2 minus 16 times 3 over 2 squared. So this is 4. 48 divided by 2 is 24. 24 times 3, that's 72. Then minus this. So 3 over 2 squared is 9 over 4. Then multiply by 16. 16 divided by 4, that's 4. 4 times 9, 36. So 4 plus 36 give us 40. So the maximum height is 40 feet. And when does it happen? It's 1.5 seconds later. Let's see this question. We want to plant a rectangular garden. Rectangular garden means this, like a rectangle. Along one side of a house. So imagine this is a house. So with a picket fence on the other 3 sides of the garden. So we need to have these 3 sides. Find the dimension of the largest garden that can be enclosed using 40 feet of fencing. What does it mean? So that means this side plus this side plus this side is 40 feet. So if we call this, let's call this x, right? We don't know this one. Let's use length and width actually. Let's say this is width, this is width, this is length, right? So the only thing we know is L plus 2W should be 40. So the total fencing is 40 feet long. So what else we know? We also know the area of this rectangle is L times width, right? The area just multiply those 2 dimensions. But we need to form a function. So how do we form a function? We're going to use those 2 equations. So let me write them together. So we're given these 2 equations. So we know that length plus the 2 sides of the width equals 40. And we know the area calculated as length times width. So now what do? We need to come up with a function. So fourth equation, we want to rewrite L as 40 minus 2W. So we just move 2W to the other side or subtract 2W on both sides. Then we substitute this L into the second equation. So now we're going to rewrite this L as 40 minus 20W, then multiply by W. So 40 times W, 40W. Then 20W times W, 20W squared. Downward parabola. Downward parabola. So we want to find the value gives the largest area. Again, this point. We need to find this point. So what do? So this is a function A of W. Right? A of W. So we want to find the derivative of A, then set to be 0 to solve for W. So that's 40 minus 40W. Then we set to be 0. So obviously W equals to 1. W equals to 1. Oh, hold on a second. It's 2W, not 20W. No wonder we're feeling this answer looks weird. I have a typo here. That's 2W, not 20W. That's 2W squared. So this is 4W, not 40W. So W equals 10. Right? W equals 10 feet. So that's the width. So width equals 10. Now, if we know width, we know the length. We use this equation. So L equals to 2 times 10. L plus 2 times 10 equals to 40. So L equals to L equals to 40. This is plus. Minus 20, which is 20. So the length is 20. Width is 10. So that's the dimension. So dimension means the width and the length. So the width is 10, length is 20. Okay. So if we ask what's the largest area, right, we just multiply by these two, 200 square feet. Okay, sometimes we like to minimize our cost in business. Right? So this question is saying, you're building 600 square feet rectangular again. Right? We even see the picture down here. Let's actually see the picture. You see it on the bottom, right? Then, so 3 sides of the enclosure will be built of redwood fencing at a cost of $14 per running foot. The 4th side will be built of cement blocks at a cost of $28 per running foot. So find the dimension of the enclosure that will minimize the total cost of the building material. Right, so what do we know here? Let's write it down. So total, we know the area equals to 600 square feet. That's given. Right? And we know the cost of wood is $14. The cost of cement is $28 per foot. That's all we know. Right? But we're going to use something we have learned previously. So if I know the area, that's length times width. Oh, I think that's one more condition. Okay, actually that's it. Let me erase this. Right, let's write here. So we know the area is a 600 square footage. We know the wood cost $14 per feet. And we know the salmon costs $28 per foot, right? Okay, so let's write it down. The area equals length times width, which is 600. Okay, the textbook called XY. Let's use XY. We know X times Y, you see Y here, X times Y is 600. Then the cost function, let's make the cost function. So the cost function, let's just write down the cost. The cost equals to, well, we only have one X. So this side only segment to be this X, right? X long, but each is 28, so 28X. And the other three sides are the same. Other three sides is Y plus X. So it's Y plus X, right? Because this is X, this is Y. Then multiply by 14. So let's write 14 here. So simplify this, I have 28X plus, I have 2Y times 14, that's 28Y. Then plus 14X. So total, what do I get? I get 28X plus 14X, that's 42X. Then plus 28Y. So we see the cost, let's write it in C. The cost depends on the length and the width, right? So what do? We're going to use this one. So we're going to rewrite Y as we divide by X on both sides. 600 divided by X. Then we can form a function in terms of X. So at 42X, then the Y, we're going to substitute this value. So 600 divided by X. So which is 42X plus, or 28 times 6, 16800, or X raised by -1. Right, to minimize the cost, we need to take a derivative. We want to find C prime of X. That's 42 minus 16800 X raised by -2. And we want to set this one to be 0. So we get a 48 equals to 16800 divided by X squared. Well, multiply by X squared on both sides, so get this. Then we divide by 42 on both sides. Let's see 16800 divided by 42. Bingo, 400. Beautiful value. So X squared equals to 400. Then we square root. Because this is a live application, we don't take a negative value. So X equals to 20. Right. X equals to 20. Once we know X, we know Y. Because Y equals to 600 divided by 20, which is 30. All right, so that's how we find. You see, again, we're given two equations. We can form the cost function equation, we can form the area equation. So we use one equation to solve another variable, substitute into a second one. Then we make a function. Then we take a derivative of the function. We set to be 0. We solve for the variable. So this one is similar, solve, maximize the volume, just what do you call it? The equations are a little bit different, formulas are different. Okay, let's see. Section 6. Let's see this example. A supermarket manager anticipates that 1,200 cases of frozen orange juice will be sold at a steady rate. The rate does not change during the next year. So we can imagine this a linear function. Right? The manager plans on ordering these cases by placing equally spaced orders of the same size throughout the year. Given that it costs $8 to carry one case of orange juice in inventory for 1 year, rate of change, right? Find the carrying cost if 3 cases. The manager places only 1 order during the year, 2 orders during the year, or 4 orders during the year. So the first one, plan costs for 1,200 cases all at once because they only order once. So the inventory of frozen orange juice in this case is a linear function. Add 1,200 and decrease steadily to 0 during this 1 order. So at any given time during the year, the inventory is between 1,200 and 0. So the average rate of change. So basically we have 2 points here. So there are 1,200 divided by 2 or 600 cases on average in inventory. So since the carrying costs are computed on the average inventory, the carrying cost in this case, it's just, $8 multiplied by 600, so 4,800. So the second is the same thing, right? It's just similarly. Okay, so let's see where we use derivatives. Let's see the second example. Still the inventory control. Suppose that the manager in example 1 wants to establish the optimal inventory, right? The key word is optimal. Optimal, maximize the profit, minimize the cost. That's the hint, involves derivatives. For the product, again, it's estimated that the total 1,200 cases will be sold at a steady rate during the next year. The manager plans to place several orders of the same size spaced equally throughout the year. So we want to use this given data in 1 and 2 to determine the economic order of quantity. So we want to see how many should he order. The order size that minimize the total ordering and the carrying cost. Right. So the first one is the ordering cost for each delivery is 75. Right? Rate of change 75 per delivery. 2 costs $8 to carry 1 case of orange juice. Since we're not given the size of each order, we need to find it, or the number of orders that will be placed throughout the year. We let X be the order quantity, and R the number of orders placed during the year. So the number of cases in inventory declines steadily from X cases, right, until 0. Also the order. So if we want to imagine something like this. So we can form the inventory equation, inventory cost, right? So 1 cost from ordering. So each order costs $75. For R many orders, 75 times R, 75R. So that's the ordering cost. What about carrying cost? Each one costs $8. but then x divided by 2. A divided by 2, that's 4. So 4x. So the total cost, inventory cost. So we can write C cost as C equals 75 times our number of orders plus 4 times the quantity, the order quantity. And also, since there are orders and X cases of each, the total number of cases in a year, remember the spending is, the estimated spending is 1,200 cases, right? So each time each order X quantity, and how many orders? So this multiply together, the 1 year ordering is 1,200. So we can rewrite this R as 1,200 divided by X. Then we substitute into this cost function. You see, this one is similar to the rectangle fencing, right? Then we get a cost function as a rational function. Then we take a derivative of this. So we take a derivative, in the end we get, then we solve for X. So X get 150, all right? Okay, let's see section 7. Right, usually in business world, we concern about the cost, concern about the revenue, and then the profit. Cost function, we use C of X. Revenue function, we use R of X. P of X is profit, how much money can be made. Is revenue minus cost. So let's see this example. Suppose that the cost function for manufacturer is given as such. So this is a cost function. In terms of the cost function, in terms of X, or X could be the quantity of a product produced. So A, describe the behavior of the marginal cost. Marginal cost means the derivative. So in business, when you see marginal, that's a hint of derivative. Then we want to sketch the cost. Okay, let's see this. 10 raised by 6, very small number, is 1 divided by 1 million. Okay, so you can think of 1 apple shared by 1 million people. It's a very small number. But this is a polynomial degree 3 because we see x raised by 3. So take a derivative, we still use the power rule. So we just get a 3 times 10 raised by -6 x squared minus 2 times 0.03006 x, then plus 5. Okay, so this is just a very small number, right? It's a very small number. But even it's a very small number, it's a positive. It's a positive, right? Then maybe we can solve this. So what do? Let's multiply. It's going to be a little bit difficult to solve because it's 10 raised by -6. It's better to use a quadratic formula because we want to sketch the graph, right? To sketch the graph, we need to know the x-intercept, the y-intercept, is a function increasing in the interval. To solve this, we'll get x values. We've got two x values. Two x values give us three intervals. Two x values will be, one will be maximum, one will be minimum. But for x raised by 3, the coefficient is positive. Usually the behavior is this. Right? The behavior goes like that. So when we sketch, we need one easy piece is the y-intercept. Right? Let's see if this is 1,000. So we have the y-intercept. So the function goes somewhere like that. Then wiggles at somewhere. Because this number is too annoying to calculate by hand. So I'm gonna go with a textbook. So take the first derivative, take the second derivative. Remember, second derivative tells us concave up, concave down. So once we do that, we get these points. We get the minimum point at 1,000, 2. And if we find the concave down, concave up, we see from 0 to 1,000 is concave down. From 1,000 up is concave up. The inflection point is 1,000, 4,000. Don't worry about this kind of question, all right? This kind of question won't happen in the exams because the numbers are too annoying to calculate. So revenue function, so the price multiplied by the quantity. And when we talk about marginal revenue, that also means the derivative of the revenue. Let's see this question. We want to minimize cost, maximize revenue. So this one saying the demand equation for a certain product is this, $1,000 in $1,000. So this is the price. Right? So find the level of production that results in maximum revenue. Remember, revenue of X, depending on the quantity, right? Equals to price multiplied by the quantity. And this X is the quantity of product. So the price is a function in terms of the quantity. We can see from here, the slope is negative, which means increasing, hold on a second, is X price or quantity? X should be quantity, right? Which means the increase the quantity, the price should be coming down, right? The lower the price is, the bigger the quantity is. So those two have, you see, P and X has a negative relationship. The slope is negative half. So we just form revenue function, which is X multiplied by price. Well, the price is 6 minus half X. So we have this downward parabola again. We want to find this point, maximize the function value. So what do? So then we take derivative, like, so the marginal revenue. So we take a derivative of this, we get 6 minus half times 2, which is 1 minus X. Do we need to graph it? Right. So it's set to be 0, we can solve. We set this one to be 0 to solve for this point. So obviously X equals 6. Then we plug into the function R of 6. So we get 6 times 6 minus a half times 6 squared. 6 is 6 squared. So we see that's a half of 6 times 6. Well, that's 3. So we get 18. So that's how we get this point. Okay. So to produce 6, that will maximize the revenue. So this is similar thing set up a demand. So given something priced at $7 per person had an average demand about 1,000 customers per week. When the price lowered to 6, the weekly demand jumped about 1,200. Assuming the demand equation is linear, find the total price that should be charged per person to maximize the total revenue each week. Right? So what are we given? We're given first point, if it's $1,000, the price is 1,000 tickets, $7, sell for $7. If we lower the price to $6 and it jump to 1,200, so we're given 2 points. We're given 2 points. We're given 2 points, of course, we can find the slope. And we can find the equation of the line. So remember we have y minus y1 equals slope times x minus x1. And we have these 2 points. The slope just rise over run. 7 minus 6 is the difference in y value divided by difference in x value. Yeah, that's a slope. We can use either point as x1, y1. So we find the price formula as a linear equation. So the price equals to 12 minus 1 over 200 of x. So again, you see the price and the tickets are in negative relationship. Right? One decreases, the other increases. Then we multiply this price by x. Right? How many tickets would be the ideal one, ideal quantity. Again, we see downward parabola. We see downward parabola. How do we know downward parabola? Because the coefficient of x squared, which is called the leading term, the leading term is negative. We take derivative, right? So get this. Then we set this one to be 0. We solve it. So we get x equals to, what is it? It is. So x equals to 1,200. Okay. 1,200 is the ideal number of tickets being sold to maximize the profit. So profit function equals to the revenue minus the cost. Let's see this question. Well, given a price function, you see price function also in terms of x, right? You could think of this as a p of x. Now given cost function, also linear function. We want to find the value of x that maximize the profit. So profit equals to revenue minus cost. How do we form revenue? Revenue is the quantity multiplied by price. Right? Well, price is a function of x. It's 100 minus 0.01x. And the cost function is also, that's cost function, minus 50x plus 10,000. So that's our revenue function. Maybe you can simplify a little bit. Well, 100x minus 0.01x squared minus 50x minus 10,000. Well, 100x minus 50x, that's 50x. Right? Minus 0.01x squared minus 10,000. Usually we like to write in order. We write like the leading term, we write up front. Well, 50x is positive plus minus 10,000. So that's a revenue function. Right? That's a profit function. The revenue function is just this, X times P. We can even go further to see, maybe next question, to see how to maximize the profit. Oh, actually, indeed. Right? So we have this profit function. Right? Then we can do P prime. We can take a derivative of this. Again, the number is too big to calculate. We set to 0 to solve it. Then there's a 2,500, right? To sell 2,500 of them. And the maximum profit is 52,500. So this shows how to calculate. Okay, they add something else. Okay, so that's about it. So today, and we see how do we use in life, what's important thing for us. Important thing for us is, we minimize cost. Because usually cost function is upward parabola. To minimize is to find such point, right? So the derivative at this point equals 0. To maximize profit, usually we have downward parabola. We need to find this point. Also depend on the situation, right? Maybe when we want to fencing 3 sides, make 3 sides of fencing. We know the length of the total fencing. So what is the maximized area? Or we know the area. We know the cost of the material. And we want to find the minimized cost. Or maybe we know the revenue, we know the cost, and we want to find the maximum profit. So so all of them is to just use the idea of derivatives, but we need to know the formula, how to come up with a formula, how to find the parameters of this rectangle, how to find the area of this rectangle. Okay, and also this formula. And what is the revenue function? That's the quantity multiplied by price. So yeah, that's for these sections. Okay, section 5, 6, 7.